Okay, here's our last big new theorem. In this case, the setup is that we have a solid E, and it's bounded by a closed surface S with an outward normal N. And then F is any 3D field. So then what we have is the triple integral over E of the divergence of F dV is the double integral over the surface of F dot ds. And this is called the divergence theorem. This quantity here on the right is called the flux through S. It represents an amount of stuff going through the surface at per unit time. So you imagine an amount of fluid, a volume of fluid coming out at unit time, or something like that. So the point is that, again, certain things are easier in one form than the other. So if you have a box, right, that's really easy for triple integrals. So that's probably the easier choice. But if you have a sphere, well, it could be either, but it's very easy to parameterize. So f dot ds may be easier. Okay, and then we use this to characterize the divergence. This gives us a little insight into what divergence really means. So if you have a field where the arrows are mostly pointing inward at a point, okay, that means that the flux is coming inward, and that means that the divergence is negative. And we say this point is a sink, so water's flowing in. And then the opposite situation where the flow is outward, the flux is clearly positive. And according to the theorem, the divergence must be positive. We call this a source.